Hi, this is Raphael Mudge, the creator of Cobalt Strike. Welcome to Part 2 of In-memory Evasion, a payload's life. In Part 1 of this course, we covered the properties of processes, threads, and memory, and anomalies in these properties that make it possible to detect memory-injected DLLs. And I hope, as I was going through that material, you didn't just accept those anomalies as a universal hard requirement of an offense process. I hope you asked yourself, why do these things work? Why are these tells present in an offense process? And that's what we're going to talk about in this lecture. We're going to use Cobalt Strike as a representative offense platform, and we're going to discuss the different parts of Cobalt Strike's offense process and why those parts of the offense process trigger the conditions of those heuristics, okay? And what I want you to take away is, in some cases, those heuristics are a hard requirement of a TTP. And in other cases, they're not. And I want you to be aware of which is which. And that's the point of this lecture. So today we're going to cover staged payloads, stageless payloads, Cobalt Strike's artifacts to get a payload in memory, and we will also talk about process injection and process hollowing. It's a lot of material, but it should be fun. Let's start our discussion of staged payloads with what is a stager. A stager is a tiny program, sometimes written in hand-optimized assembly, but not always, that downloads a payload and passes execution to it. That's it. Stagers exist as a way to ship code that bootstraps a payload with an attack that doesn't have a lot of space to contain the full payload. Okay, so it's merely a convenience factor. When you're dealing with staged payloads, the process to get a payload in memory broadly looks like this. The first step is that something, some artifact, maybe some exploit, runs the payload stager. The payload stager downloads an encoded payload. We download an encoded payload because if the payload is not encoded, then it's likely to be picked up going over the wire and flagged as malicious. So encoding is an obfuscation step. The encoded payload is then run, and the encoded payload decodes the payload like beacon in place. Execution is then passed to the payload itself, which initializes itself and runs. These are the 4 steps in the offense chain when dealing with a payload stager. Now, we expand that a little bit. The artifact or exploit, whatever it is that's running the payload stager, is responsible for steps 1 through 3, which involve allocating memory for the stager and creating a thread or passing execution to the stager in the current thread, one of the two. All right? So right away, allocate memory, create thread. Everything we're talking about in this course involves the properties of processes, threads, and memory. So it should be a big red flag to you. Those things are important. That artifact is responsible for a lot. Steps 4, 5, and 6 are the stager being executed itself. Notice in step 4, the stager allocates memory for the encoded payload. That's another place where we could do it in a wrong way that triggers some sort of heuristic. In steps 7 and 8, the encoded payload is decoding itself in place. And steps 9 through 11 are the payload initializing and passing execution to itself. So the payload's embedded loader is responsible for some of our characteristics in memory as well. Let's take a look at the process to get a payload in memory with the help of a stager by actually looking at the ground truth of that process. Here we are in Cobalt Strike, and I'm going to go to Attacks, Packages, Microsoft Office Macro. And this attack is going to generate a VBA program that I can run via Microsoft Word or Excel. So I'm going to copy that macro to my clipboard and come over to my target, where I will open up Microsoft Word. And I'm going to follow the typical steps to add a macro to a document. So I'm going to go to View, Macros, View Macros. I'm going to create the macro in the current document. Start with a temporary name of blah, clear this content, and paste in the macro. Okay. This macro is the artifact that will run the payload stager that downloads our payload. Let me show you what's happening here. This array of bytes is the payload stager. We use a payload stager with the macro because the macro can't accommodate a very large payload this way. This macro happens to spawn a temporary process. That's what you see here with run stuff. We're calling run stuff with the path to rundle32. And this macro allocates a 4 kilobyte page with read, write, execute permissions in that new process. It then copies our stager over to that temporary process and calls create remote thread to kick off the code in that stager in its own thread. So again, the artifact that delivers the payload stager is responsible for a lot of our offset characteristics. I'm going to go ahead and close that. And I'm going to save this document as a macro-enabled document, just so we can take a look at this. We'll just call it example.docm. Hit save. And let's close the document. And let's open it. And let's do what everyone should do when they open a Microsoft Office document, and that is press Enable Content. And if we come over here to Process Hacker, we can see winword.exe with a child of rundle32.exe. Okay. And we know why this is, right? Because we saw that the macro runs rundle32.exe and injects our code into it. Now, let's follow the rest of the attack chain and code, and we'll come back here. Let's come over here to Cobalt Strike in Kali Linux, and there we go, process 3340. Okay, good. So I mentioned that the artifact, the macro, runs our payload stager. Well, let's look at the code for a payload stager. This is the code, for an HTTP stager from the Metasploit framework. The stagers in Cobalt Strike are derived from the stagers in the Metasploit framework for the most part. And no big surprise, this particular stager happens to load WinINet and call the necessary calls to connect to my web server and download the encoded payload stage. The offset characteristic that the stager controls is the memory allocation. Okay? Here, ignore that, ignore the comment I mean. Here, it happens to call virtual-alloc with a 4 megabyte length and read-write-execute permissions. Okay? And you may be asking, why read-write-execute permissions? Well, because the stager expects to receive an encoded stage. An encoded stage is a blob that will decode the payload in place and pass execution to it. And so because it expects to receive that blob, the encoded stage needs memory that it can read from, so it can read from itself. It needs to be able to execute because it itself is a program, and it needs to be able to write to itself because it's decoding itself in place. So here, because of the steps we're taking, read, write, execute permissions are necessary. Now, in a future offense universe where hackers are aware of these kinds of characteristics, could staging be redesigned to avoid the need for RWX permissions? Certainly. I mean, it's possible to make the stager contain the decoder as well. There's a lot of things a clever programmer could do, but this is why things are the way they are today, is because the stager and the decoding process or decoding stub are separate. Okay. Decoding stub. What do I mean? Well, Cobalt Strike encodes the beacon DLL when it sends it over the wire. And it does this because we don't want the beacon DLL going over the wire unobfuscated. There are signatures that will pick up a DLL just going over the wire. It's a really bad sign. Here's what it looks like to encode the beacon DLL, or really any blob, but we use it for that beacon DLL. Cobalt Strike generates a random value and just walks over every 4 bytes of the beacon payload and just XORs it. Just applies a XOR operation by that random key. That's it. Very simple XOR stage encoder. Now, an encoded blob by itself is not an executable thing that decodes itself in place, right? Hope you wouldn't think that. It needs a decoder. So Cobalt Strike prepends a stub to the beginning of this encoded blob. And that stub simply queries its own package itself for the current size, the key, and it simply walks over the stuff after the stub and decodes it in place and then passes execution to it. That's it. And if you're curious, I mean, this is what one of the decoder stubs for beacon looks like. Just nothing too fancy, just a loop and applying a XOR mask. Okay, so this is our encoded payload being decoded in place. After this step is complete, execution jumps to the blob that is the reflective DLL. The reflective DLL is prepended with code that calls something called the reflective loader. The reflective loader is a function that is mixed inside of the beacon DLL. And the reflective loader function happens to come from the reflective DLL injection project by Stephen Fewer. So the DLL basically forces, or the DLL package forces a call to this reflective loader with a pointer to itself. And that's significant. When we look at the source here of the reflective loader, this will make a little more sense. So we call the reflective loader with a pointer to ourself. What does that mean? It means this function will start walking the DLL it is a part of and initializing that DLL for execution in a new part of memory. And that new part of memory happens to be allocated here, right here. So we happen to allocate a new base address for our DLL. That's the reflective loader is doing that. And we're using virtual alloc to do it. And the default reflective loader happens to use read, write, execute permissions. So this loader does the same thing load library would do, except it's operating on a arbitrary blob, in this case itself. And I should say almost the same thing load library would do. Load library doesn't actually use read, write, execute permissions for all parts of DLL. That's a shortcut that this particular code takes, okay? But that's why you see the reflective DLL with RWX permissions in memory. Is that making sense so far? Well, let's go back to the target and let's examine rundle32.exe real quick. And remember, the properties of a process do matter, right? Like in terms of trust. So rundle32, signed by Microsoft, that's great. But its parent is winword.exe, probably not so great. And rundle32 is also the favorite whipping post of offensive tools, so that makes us a little suspect too. Process indicators. Now let's talk about threads. We do have a thread not backed by a module on disk, and that was created by our artifact, the VBA macro, with create remote thread. If we go to memory and let's sort by protections, here we have 3 blocks, okay? And I pointed out a similar series of 3 blocks in part 1 of this course, but now we know why they exist. I hope I'm making it real to you. We have 4 kilobytes, and this is the stager, right? This is the code that downloads our payload and passes execution to it. Or I should say downloads our encoded payload. And it happens to allocate a 4 megabyte block with read, write, execute permissions. And here, because no stage encoder is involved, you don't see the stub, you just happen to see the beacon DLL. And that's an artifact of the trial versus the licensed product. But the reflective DLL that we downloaded and passed execution to here happens to initialize memory for itself and happens to think it should be 268 kilobytes because that's what the DLL says in its size of image field. And this has RWX permissions because that's what the reflective loader happened to set up for us. Okay, makes sense? So that's why we're seeing what we're seeing. Pretty cool, right? So that's an example of the OPSEC characteristics of a chain to get a payload in memory with a stager and why those OPSEC characteristics are the way they are. All right, we covered payload staging and what it looks like to get a payload in memory with a stager. What if we don't use a stager? Well, that's a stageless payload. A stageless payload is an artifact that contains the entire beacon payload without a stager. The offense process for a stageless payload is a lot simpler. Something, your exploit, your artifact, whatever, runs the payload stage. The payload initializes itself and runs. That's it. Here's what this looks like compared to the process for dealing with a payload stager. Steps 1 through 3, the artifact allocates memory and passes execution to the payload stage. What I want you to take away from this is your artifact has a great deal of control over the OPSEC of your payload in memory. So how you get there is going to be the deciding factor most likely. Steps 9 through 10 is the payload stage, allocating memory for itself, initializing itself in that new memory, and passing execution to itself. That's it. That's a stageless payload. In Cobalt Strike, you can export a stageless payload by going to Attacks, Packages, Windows EXE S, as in stageless, and there's actually a number of output options. You can do an executable, a DLL, a raw position independent blob, a PowerShell script. Several things are right here. You can do a 32-bit or 64-bit stageless payload with Cobalt Strike. Okay, let's take a look at stageless payloads. Here I am in Kali Linux, and I have the Cobalt Strike licensed version. I have the licensed version because I want you to see that the things I will talk about in a moment in this presentation are true. I don't want you to think I'm lying to you. I'm going to go to Attacks, Packages, Windows Executable S, and export a stageless beacon payload. And I'm going to go ahead and host it for fun. And I'm going to go ahead and run this over on my target. So here we are on the target. Actually, we'll just open up Internet Explorer. And let's run beacon.exe. Let's give that a moment. We should see in Process Hacker, there's beacon.exe, which is a child of Internet Explorer. And let's go ahead and double click. And let's come over to the threads. All threads backed by a module, because the artifact controls the thread. And the executable has a lot more control or does some more better things or more normal things than the macro did. So that's why our threads look normal, at least using this particular heuristic. Let's come over here to the memory. Sort by protection. And we now have one read, write, execute block. We don't have a 4 kilobyte block because there's no stager. We don't have a 4 megabyte block allocated by a stager because there's no stager. We just happen to have a read, write, execute block that has our beacon payload in it. Okay? And that read, write, execute block, that characteristic, is controlled by the reflective loader. So what I want you to take away from this is we have an artifact that does things a little bit more normally. So we happen to have a normal thread, nothing fancy, weird, or offensive. And we happen to have a block where our payload lives that has characteristics we don't like, but those characteristics are controlled by the reflective loader. And we'll talk about our options for dealing with that in part 3 of this course. In case you can't tell, I'm not a big fan of payload staging. Staging is brittle, easy to spot, easy to disrupt, and in the case of this course, has many indicators we would prefer to not have. It is possible with Cobalt Strike to reduce the amount of payload staging in your operations. You can use stageless payloads for most things. I wrote a blog post on this back in 2016 called Talk to Your Children About Payload Staging. That blog post contains my advice for how to adjust your operations to take advantage of stageless payloads over actions that happen to use payload staging. I highly recommend looking at it. Again and again, I keep saying the artifact that delivers your payload or payload stager has a lot of influence on which heuristics you have to worry about. This chart shows the different kinds of artifacts produced by Cobalt Strike. Artifacts that Cobalt Strike uses to get the beacon payload or a payload stager into memory. These characteristics are just a snapshot. They could be different in March 2018 and later. It's also very possible that if I were producing this chart in January, say, 2019, that the OPSEC considerations might be worded differently. For example, I might not really care about the RWX permissions. I might care more about how the memory was allocated, virtual alloc, heap alloc, or stomping over the memory of something already legitimately loaded. We'll talk about some of the possibilities in the next lecture, but I want to emphasize that this area is constantly moving, and this is what the OPSEC characteristics of Cobalt Strike's artifacts look like in February 2018. There's some good news here. What's that good news? Well, you control everything in that previous chart. Cobalt Strike has a variety of kits, profiles, and scripts, a variety of ways you can customize the tool set. The Java applet and its indicators are in your control via something called the applet kit. The executables and DLLs are in your control through the artifact kit. And the Visual Basic for Applications macro, the PowerShell templates, and the Python template are all in your control through the resource kit. So if you have a better way to do any of those actions and do them in a more OPSEC safe way, you can bring that into Cobalt Strike pretty easily. And I very much encourage you to do that. And if you'd like to learn how to get started with that, I recommend you take a look at the blog post on this slide. Everything in this lecture so far has focused on getting a payload into memory. When you're using the payload, the biggest concerns you should have as far as these memory indicators relate to process injection and process hollowing. Let's talk about those now. Here's what it looks like to do process injection in Cobalt Strike. The beacon payload allocates memory in a remote process, copies the program it wants to run in that remote process to it, and creates a thread in that remote process to run the program. And the program can mean a payload stager, it can mean the beacon payload, or some other capability compiled as a self-bootstrapping reflective DLL. Here's where you're going to encounter process injection in Cobalt Strike. The DLL inject command, the inject command, and shinject command all inject capabilities into a remote process. Some of Beacon's post-exploitation jobs can also be targeted to a specific process. And if you're using them that way, you will know because you're telling Beacon a process ID and an architecture. In these cases, you know you're doing process injection. What about process hollowing? In Cobalt Strike, process hollowing, it's kind of a poor man's version, if you will, is allocating memory in a remote process, copying a program or capability to that remote process, and hijacking an existing thread in that remote process to run the copied program. In Cobalt Strike, you see process hollowing with Beacon's post-exploitation jobs. Many of the things you do with Cobalt Strike don't actually live inside a Beacon. Instead, Beacon creates a temporary process, copies the capability to run into that temporary process, runs it by hijacking the main thread of that temporary process, reads the results from that capability over a pipe, and then kills the temporary process. Cobalt Strike does this for a reason. Historically, it had very little to do with OPSEC. It had everything to do with stability. The idea is if a capability crashes, you don't lose your payload. You don't lose your foothold on a system. That's why Beacon tends to externalize its functionality in this way as much as possible. When are you using this mechanism? Well, a lot of commands in Cobalt Strike run post-exploitation jobs this way. Hash dump, Mimikatz, the port scanner, screenshot, the desktop command, power pick, all kinds of things. You'll see this everywhere in Cobalt Strike's actions. Let's talk about the OPSEC characteristics of these actions. Process injection. For the most part, with process injection, you are safe from RWX pages. If, huge if, you're injecting from the same architecture to the same architecture. So if you go from a 32-bit process to a 32-bit process, you're fine. If you go from a 32-bit process to a 64-bit process, all bets are off. Cobalt Strike uses different, more hacky kinds of actions to actually run your payload that are going to have worse OPSEC characteristics. With process injection, the way Cobalt Strike's Beacon does it, you will not have a thread backed by a module. So be aware that the process injection commands happen to have this negative OPSEC characteristic. What about process hollowing? Process hollowing in Beacon happens to have much better OPSEC characteristics. But again, I want to emphasize only when going from the same architecture to the same architecture. When you start going to different architectures, like going from 32-bit to 64-bit, it can be bad. Cobalt Strike will fall back to process injection characteristics. But the process hollowing does work 32-bit to 32-bit, 64-bit to 64-bit, and 64-bit to 32-bit. So works in most cases. In general, if you're careful, process hollowing is fine in terms of RWX pages, and because it's hijacking an existing thread, you happen to have a thread with good characteristics. So that's how these two behaviors stack up against the things we've talked about. If you're curious for a more comprehensive list of which Beacon commands inject into a process and which ones spawn post-exploitation jobs and take advantage of process hollowing, I recommend you read OPSEC Considerations for Beacon Commands. This particular blog post happens to break these things down for you. In this whole discussion, I want you to remember something. We're talking about process injection, process hollowing, artifacts, right? Those things are responsible for getting a capability or getting a payload like Beacon into memory. So they control steps 1 through 3 here. The capability, its reflective loader, happens to control other characteristics. With the Beacon payload, you actually have some control of those characteristics. We'll talk about that in the next lecture. For capabilities like Mimikatz, hash dump, and others, that control is not there yet as of February 2018. So keep that in mind. It is a limitation. Also keep in mind, there's a reason that stagers are grayed out here, or the steps related to staging. And that's because staging just happens to have very bad characteristics. Avoid it if you can. That's going to be an ongoing message in the next lecture. So that's a payload's life, a deep dive into an offense platform, where it allocates memory, where it creates threads, where those things have bad characteristics by choice and by necessity. We've covered payload staging, stageless payloads. We've talked about the artifacts in Cobalt Strike. I briefly touched on process injection and process hollowing. Everything I said there is true if you're staying same architecture or working from a 64-bit beacon. I hope you've enjoyed part 2 of In-memory Evasion. Good luck, happy hacking, and I'll see you for part 3.